Okay, so remember where we were? We were talking about abstract vector. Well, the first thing that we did last time, I feel like it's a long time ago, was we talked about how to get from the coordinate vector. You're in Euclidean space, and somebody gives you two different bases, right? And then what we saw was how do you get from the coordinate vector. You have some vector, and you express it as a coordinate vector with respect to one of the bases. And there's a way to get from that coordinate vector to its coordinate vector with respect to a different basis, right? And we have this thing called the change of basis, the change of basis matrix, right? Right. Just to remind you, so recall, right? You have some basis B1 to Bn, and you have another basis B1 to Bn, also of Rn, right? And if you had some let's say that x, you have some vector, so let x be in Rn, be some vector, right? In that case, x could be written in two different ways. One is like this, b1, b2, bn, times the coordinate vector of x with respect to b. Another way is that it could be written as v1, v2, vn, times its coordinate vector with respect to v. Right? Remember what these coordinate vectors are. These are the coefficients that express x as a combination of these guys. If this thing was C1, C2 through Cn, then that would tell you that x is C1, B1 plus C2, B2 plus blah, blah, plus Cn, Bn. Okay, and then so to get from one basis to another is easy, right? To switch from one coordinate vector to another, it's easy, right? We see that then B1, B2, Bn, coordinate vector with respect to v is the same thing as v1, v2, vn times the coordinate vector with respect to v. And so to get from one to the other, you just take the inverse of one matrix and multiply it on the other side. Right? So the coordinate vector with respect to v is going to be v1, v2, vn, minus to the minus 1, xb. And that shows you what your change of basis matrix is. Right? The matrix that gets you from the b coordinate system to the v coordinate system is just the b matrix times the inverse of the b matrix. Right? Where this matrix is the one with columns that are b1 through bn, and this one is the matrix which has columns v1 through bn. Inverted. So this was the change of basis matrix in Rn. So now we're going to do the same thing in the case of abstract vector spaces. I'm going to erase all this just to restart. Okay, so abstract vector spaces. So again, the vector space, you have E V1 to Vn, a basis of V. As before, given any vector in V, we define the coordinate vector with respect to the E basis. Coordinate vector of V with respect to the E basis as, right, just the list of coefficients. Where V is C1 V1 plus Cn Vn. Maybe I'll put vector signs on these guys. To distinguish them from scalars. Where this thing is the unique expression, is the unique expression. V has a linear combination of the VI. Okay, so now we're going to do something a little bit tricky, which is the change. So, right, here we have some abstract vector space, and then we associate with it, you know, to each vector you associate some vector in Euclidean space. Okay, and this thing is the coordinate vector. So, right, so definition. So we're going to have the same problem, right? We have some coordinate vector with respect to one basis, and we want to switch it to coordinate vector with respect to the other basis. Okay. So go change a basis again, but this time in the case of abstract vector spaces. So let V be an n-dimensional vector space. Let B, namely V1 through Vn, and B prime be W1 through Wn, be two bases. Two bases of V. Okay. Let's express the V basis in terms of the B prime basis. Okay. So suppose that V1, right, is some constant times W1 plus some constant times W2 plus some constant times Wn. That V2 is some constant times W1 plus some constant times Wn. That Vn is some constant times W1, blah, blah, blah. The VIs and the WIs are both bases. So, you know, each of them, you know, anybody in the space can be expressed as a linear combination of the WIs, because the WIs are bases, and this is unique. Yeah, Mia.
Where are the S's coming from?
So, the WIs are a basis of V, right? So anybody in the whole space can be expressed as linear combination.
Okay, yeah, okay,
right?
I get it.
Right. So,
I thought you had said it earlier and I missed it.
nope, no. Right, so you just say, what's this guy as a combination of these guys? What's the second guy? What's the first guy as a combination of these guys? What's the second guy as a linear combination? What's the, right? So you're taking one basis and you're expressing it as linear combinations of the other basis. And as you might expect, this is the thing that will allow us to go from one basis to another basis. Okay. So, we figure out these coefficients, right? You have to figure out what these coefficients are. Somebody gives you two bases, and you say, oh, well, let's figure out what each guy is in one basis in terms of as linear combinations of the other bases. Okay? And you get these indices, which you use to create a matrix. So let S be the matrix SIJ. Okay. The question that we're trying to answer is how do we get from the expression, the coordinate matrix with respect to the B basis, to the coordinate matrix with respect to the B prime basis. And here's what we're going to claim: that one guy, the B prime guy, is just going to be the matrix S times the other guy. And this always confuses me, so let me see if we can figure this out slowly. So why? Okay, so let's think. Say, I need to write that. Say, let's just use put some notation down. Suppose that the coordinate of V with respect to B is x1 through xn. That is to say that V is actually, this time of the day my arm always starts to go numb. Why? Am I dying? I'm dying? Tell my family I love them. Let's see. So this means that V is x1 times V1 plus x2 V2 plus xn Vn. That's just what that means. Right? That's just definition. Right? The coordinate vector is this. In other words, V is this particular linear combination of the V's, of the VI's. Right? Okay. Well, let's rewrite that. The V's, in turn, we rewrote in terms of the W's. Right? We're trying to get this thing expressed in terms of the W's. Right? Our question is, what is the expression of V in terms of the W's? Right? So let's figure it out. It's like doing just hack work, grunt work. Let's figure it out. V1 is what? S11W1 plus S21W2 plus SN1WN. Right? And then, et cetera, et cetera. V2 is S12W1 plus SN2WN. You get xn times Vn, and Vn was S1nW1 plus SNnW1. we look at how many W's we have, right? The Wi's, if we're looking at, this is some sum of Wi's, right? Where the Wi's, we're going to get, right, for W1, we get x1, s11, x2, s12, da da da, xn, s1n, right? For W, you see how it adds up, right? So we're going to get summation, right? If I have W1 here, I'm going to have x1, 1, 2, so that should be an index, call it index j, and I have S1j, xj is j ranged from one end. Right? So that's W1, and then for Wi in general, I'm just going to have an I here. So I'm just counting. All I'm doing is counting here. I'm just rewriting. Basically, nothing has happened. Right, I've used distributivity. Okay. So that's it, right? That tells us what the coefficients are. Right? The coefficients of the Wi are these guys. Right? So in other words, right, yi, right, if we denote. So if we denote this thing by y1 through yn, we see that yi, the ith guy, is going to be summation sij xj from j equals 1 to n. Right? In other words, i.e., the vector you get by expressing the vector with respect to the b prime guy is just s times the vector times the expression with respect to the with respect to the b basis. Right, y1 through yn turns out to be s11, s12, s1n, sn1, snn, and s1, sn. Great. Everyone okay? Okay, so so you see what the transition, and so this matrix S, this is called the transition matrix from B to B prime. Notice that when you're actually calculating it, you express the V's in terms of the W's, and you have you don't take exactly the coefficients in this form, but you actually take the transpose. You notice that I wrote this actually differently, right? S11, S21, right? This is actually this thing, right? This one is here. This one is here, right? It's a transpose of what you get here. For example, suppose we are in P3, right? The polynomials of degree less than 3, and we let basis 1 be 1x squared. Basis 2 is going to be 2x 4x squared minus 2. And we'd like to go from the first guy to the second guy. So here's what you need to do. You express each, if you like, following rules. Here's a bunch of rules. You express the first basis in terms of the second basis. So you say, okay, well, 1 is going to be, 1 times 1 plus 0 times 2x plus 0 times 4x squared minus 2. You guys in the back okay?
I was just, yeah,
yes?
Good.
Okay. Sorry. Okay. And then here you get 0 times 1 plus 1/2 times 2x plus 0 times 4x squared minus 2. And here you get 1/2 times 1 plus 0 times 2x plus 1/4 4x squared minus 2. Okay, so these are, you get 1, 0, 0, 0, 1/2, 0, 1/2, 0, 1/4. Right? And you take the transpose of that to get your transition matrix, as we say. Right? So then the transition matrix, right, going from B to B prime, is going to be the matrix that's the transpose. 1, 0, 0, 0, 1/2, 0, 1/2, 0, 1/4.
How'd you get the 1/2, the 1, all those scalar stuff?
Yeah, that's from here. So remember, what is this? What is the transition matrix? It's the matrix that it turned out to be that the transition matrix was actually the matrix of coefficients that you got when you expressed one basis in terms of the other basis, the basis that you're coming from to the basis that you're going to. So you say, okay, I'm going to take the basis I'm coming from, I'm going to express it in terms of the basis that I'm going to, and then I'm going to take these coefficients, right? I'm going to take these coefficients and make a matrix out of them, right? I'm going to take these coefficients, transpose them, and get a matrix. That thing is actually my transition matrix. So here they are, right? I've expressed one basis in terms of the other basis, and here I put these coefficients, right? So I take all these things that I've circled, I transpose it, and I get this matrix that will take me from the coordinate vector with respect to B to the coordinate vector with respect to B prime. Okay, first.
Well, I understand how you go from that to that, but I don't understand how you get the coefficients in the first place.
Oh, okay. So, if you said 1 is some constant times 1 plus some constant times 2x plus some constant times 4x squared minus 2. Okay. And you want to figure out, you're asking, how do we figure out what those numbers are, right? So this is going to be a plus 2bx plus 4c x squared minus 2c. Right? That's to say a minus 2c plus 2bx plus 4c x squared. Oops. Okay. Right. Okay. And so you'd say, okay, well, if you have two polynomials, then the two polynomials that agree with each other, then the coefficients have to agree. So I know that 4c must be 0, because the coefficient of x squared on the left is 0. Coefficient on the right is 4c. The coefficient of x on the right is 2b. The coefficient of x on the left is 0. The coefficient on the right of 1 is a minus 2c. On the left, the coefficient is 1. So that tells me that c is 0, b is 0, and a is 1.
Oh.
So you just, when it's just linear algebra,
Mhm.
right? It's sort of in the lowest sense of linear algebra. Plus the fact that that if you have two polynomials that agree with each other, the coefficients have to be identical.
Mhm.
Right? Yeah. Yeah, Teresa.
Why do you have to take the transpose of S?
Well, you see, that's what worked.
Okay.
Right? When we did it, that's what happened.
Okay.
I don't have any better explanation other than that's.
'Cause
if
it's-
you didn't, you would. get
Because
it wrong.
okay, so it goes down the rows, right?
Mhm.
Then it goes across.
Yeah, so you got 1, 0, 0, so that's going to be our first graph,
Okay.
our first column. Right? 0, 1/2,
Oh,
0.
because
0, 1/2, 0.
it's an, okay, I understand.
Right. So yeah, it just I should try to think of a more intuitive explanation, but you see that when we worked it out, that is what worked. Right? That's what you got.
Right.
Right? We ended up with this, which is the transpose of this. So for example, if somebody gave you, if somebody said, what is the matrix, I don't know, what is the vector 10 plus 20x plus x squared in B prime? Then you would say, oh, it's easy. It's easy, right? I take my vector and I express it with respect to v. What's going to be, let's call it v. Well, v with respect to the standard basis is just what? 10, 21, right? Right? And then you hit that thing with the transition matrix. Right? So then S B will give you the expression with respect to the new basis. Right? So you just say, well, with respect to the new basis, it's going to be 1, 0, 1/2, 0, 1/2, 0, 0, 0, 4, 0, 0, quarter, excuse me, times 10, 21. Right? You work it out. Say, okay, I get 10 and a half, right? 10 and a half. I get 10, and I get quarter. Okay. So that tells you that this thing is going to be 10 and a half times the first guy plus 10 of the second guy plus a quarter of the last guy. What you see is right. Yeah, yeah.
For the homework, it says like E1 and E2.
Yeah.
What are those?
Is
Is it just like 1, 0?
Yeah,
instead of
yeah,
one?
standard
Okay.
basis, yeah. Maybe I didn't make this clear enough, but in Rn, so in Rn, the standard basis is written E1 through En. I didn't mention this. It's just, the first guy is 1, 0, 0, 0, 0, the second guy is 0, 1, 0, 0, 0, 0, the last guy is 0, 0, 0, 0, 0, 0, 0. Any questions? Any questions? Yeah. Might be like that. That's sort of cool. We'll take a couple of observations. One, if S is a transition matrix, then actually S is invertible. So if you think about it, why? For Sx to equal y, that means that, sorry, say S is the transition matrix from B to B prime, where B is B1 through Bn, and B prime is W1 through Wn. For Sx to equal y, one has to have y1, w1 plus y2, w2 plus yn, wn equaling x1, v1 through xn, vn. Or maybe it's better to say it like this. Sx equals y is equivalent to. Observe that for Sx equal y, that's the same thing as saying this. Right, because Sx equals y means that the coordinate vector of like this thing is the coordinate vector of something with respect to B. This is this coordinate vector of the same thing with respect to B prime. Yeah. So that's to say that's exactly this. Okay. So when could Sx equal 0? When could Sx equal a 0 vector? When could Sx equal to 0? Yeah.
When y equal to the 0 vector?
Yeah, well then this would have to, all these guys would be zeros, right? So that would tell you that, in that case, x1, v1 plus xn, vn is 0. Right? That happens, I should say. That happens if and only x1, v1, dx, xn, vn is 0. But so what? What would that tell you? x1, v1, the xn, vn is equal to 0. So
X equals 0.
so all the x's have to be 0, right? Because the vi's are a basis. They're linearly independent. Right? The only way you can get 0 is if all the coefficients are 0. Right? So all the xi's in that case would be 0. But what does that tell you? The only time you get 0 here is if x is 0. In other words, S is an invertible matrix. Right? The null space is 0. Right? So the null space of S is 0. And that tells you that S is invertible. So all these transition matrices are invertible, and you could probably guess that, because if you've got going from one basis to another basis, well, you can always create a matrix going from the other basis back to the original basis. And that matrix will be the inverse of your basis, of your matrix. So sort of maybe obvious that there is an inverse, right? The inverse is just going to be the matrix that goes in the opposite direction. It takes the coordinate vector with respect to the B prime basis and gives you the coordinate vector with respect to the B basis. In fact, a converse statement is true. If S is invertible, then S is a transition matrix. So I'm not going to give you the whole proof, but let me sort of sketch it out. Take VI a basis for some matrix, for some vector space of the right size. Okay. So let's say that S is an n by n matrix, and that V is the right size. Right? So and then you just do something very, very silly, which is you define the Wi so that W1 equals S11 V1 plus Sn1 Vn, etc. Right. Then S is the transition matrix from the VI's to the WI's. I'm sorry, from the WI's to the VI's. Okay, just like you forced it to be the transition matrix. And so it's a transition matrix. So the second statement is sort of silly. But it's true. The only thing that you need to check here is that the WI's then form a basis. That the WI's then form a basis. But I'll let you take a look at that. So, you just show that they're linearly independent, and then there's n of them, so they would spec. How do you all feel?